Now, we've talked about simple Kriging mainly to this point, but you might be saying, well, I don't always know what my average is going to be. And if I don't know the average, how am I going to do simple Kriging? And that's a great question. It's a question that motivates us to talk about other types of Kriging. So we've looked at simple Kriging so far. And I do a video where I go more in depth on these different types of Kriging. I'll post that later. But for now, let's just look at these briefly here. So we've had sigma ij times lambda is equal to sigma I naught. And you can kind of see some combinations of those different variables here. If we were interested in just estimating the mean, so one thing that we could imagine doing is estimating the mean using the Kriging equations and then subtracting that mean and using simple Kriging. So we could get the mean by using this set of equations where we have the same sigma ij that we had before. Again, this capital sigma ij never changes. It's based on the data that we have. And so sigma ij is always the same. But now, well, we still have lambda there, but now we've added this, we've sort of augmented this matrix with a column of ones here. This one means that there's a whole column of ones, which is the same size or the same number of rows as sigma ij has rows. Here's that same thing transpose. So that transpose means this is a row vector, and it has the same number of columns as sigma ij has columns. And then we just have a 0 here in this corner. And then we've got this additional minus nu term here. And you can see we've got 0 and 1 over here, so there's no sigma I naughts over here now. We don't care about a new particular location. We're looking at the overall mean. And this system of equations, again, I go through the derivation of this more in the other video. This particular set of equations, if we solve it and we use our lambdas, plug them into the expression that we had before, this expression here, let me just copy this and pull it over so we can compare directly. So our equation is always the same. We're going to take a weighted average of the data. In this case, we're estimating an average from these lambdas, which are now no longer the simple Kriging lambdas. These lambdas are different. And if we were to plug these lambdas into this expression, we would no longer get z star, but we would get an estimate of the mean of all the data. And again, refer to the other video for deriving why this is the case. But now it should be pretty simple to see if we just look at this. So this gives us the mean, which we don't know. And now if we compare to this set of expressions, well, now we still have sigma ij. We've got this augmented matrix here. We've got lambda and minus nu. And then now we have, instead of 0 and 1, we have sigma I naught and 1. This should look very similar to our simple Kriging equations, where we had sigma ij times lambda times sigma I naught. And so basically what you can see is we've combined simple Kriging with Kriging of the mean in some way. And again, this is derived in the other video. We've combined them together, and now we can estimate a value. If we plug these lambdas into our expression now, we can estimate a value at a new location when we don't know the mean. So ordinary Kriging allows us to estimate what our value should be or interpolate our data when we don't know what the mean is, with an unknown mean. And we've done it by essentially combining this Kriging of the mean with simple Kriging. A little more complicated than that, but I'll refer you to the other video for the details. Now you say, well, my data doesn't necessarily just have a mean that I don't know. It has a trend that I don't know. It has perhaps a linear function of x and y, or maybe a function of topography, or time, or some other space-type variable, where we have some unknown trend that we need to estimate in addition to our spatially covariant part with zero mean. And so that's where universal Kriging comes in, and you can see it looks exactly the same as ordinary Kriging, except for we've replaced all the ones now with these capital F's, and this lowercase f here for the one on the right-hand side. And these F's are basically the spatial model for the drift. And I'll use drift and trend interchangeably. Usually people like to say drift for Kriging for some kind of spatial basis functions that they're using in addition to the spatially correlated part. For me, drift and trend is the same thing, so I'll just say either one. But this is could capture a linear function of x and y, for example. And what does that look like? Well, I show an example on the Canvas page, but you would just have, for example, a column of 1s, a column of x's, and a column of y's. And that would be your linear function in x and y. And then here in this little f, you would have your 1 and x and y value of your new point location, wherever that's located. And so you would solve for then this system of equations, which again gives you the lambdas. And in this case, actually, this new here turns into a vector, so we have a whole vector of new values. But either way, we would solve this expression for lambda and nu, and then we would take our vector of lambdas, just like we've done before, plug them in here, and calculate what the weighted average of our data is, given these lambdas that we've calculated with universal Kriging, which are going to be different from ordinary Kriging and Kriging of the mean and simple Kriging. So I hope you're getting the picture here. We're solving for the weights that we need using data correlations, sometimes linear basis functions, sometimes just a simple non-zero mean. Sometimes when the mean is 0, we're solving for a set of weights which we can use then to calculate our new estimated value. And the expression for calculating the new value is always the same. It's always a weighted average of our observations. But how you get those weights is going to be different depending on if you have a 0 mean, if you have an unknown mean, if you have an unknown trend, which is a linear function of your space variables. So you can do different things. You can solve these systems with those different types of assumptions, but the final expression is going to be the same, just a weighted average of our observations. But what have we accomplished? We've accomplished being able to account for spatial correlations in the data, spatial anisotropy. We've accounted for closeness from the data to our new point location, if that's what we're doing. We've accounted for redundancy in the data and clustering. And Kriging will give us the best estimate, best in the sense of minimizing the estimation variance. In other words, the squared difference between our value, our estimated value, and the true value is minimized. Kriging gives us that best value, accounting for all of these things. Now, one more thing I want to cover in this particular presentation is what if you had to do it at several locations? In other words, what if you had a whole grid of points, right? Because this is how practically this works. We want to estimate a whole grid of values. We want to map, basically. Based on some data, let's interpolate and get a whole map of predicted values and also uncertainties. Well, that's very easy to do, and I'll just illustrate it here with the simple Kriging equations. We can simply stack up each one of our covariance terms, where here this is the covariance of all our data with our estimation location at the first estimation location, second estimation location, third estimation location. So here now I've sort of used the superscript to denote the particular grid node. So I have a whole grid, and I can just march through here, take the covariances for each one of these estimation locations with all the other data, use that to populate this matrix of, this is now a whole matrix now instead of just a vector of covariances. And I will get, if I solve this system, again, I'll know this term doesn't change. This term is going to be based on my whole grid of points now. And I can solve for a whole matrix of lambdas, where each column of the lambdas now corresponds to each one of my new estimation locations. So if I have a grid, let's say from 1 to 9, a 3 by 3 grid, I'll have this matrix will end up being 3 rows by 9 columns. And I'll have, 3 rows by 9 columns of lambda. So in this case, I've got just 3 estimation locations, and I have 3 columns here, 3 columns here. And I could solve this system. I'll get a whole matrix of lambdas, and then each column, I'll just pull that out and use it in the same way as we have before. Each lambda, I'll multiply by each set of our data. Each set of lambdas I will multiply by our data, and that will give us our estimated value at each grid node. So that's all for this video. In the next video, we're going to do a simple example where we look at an Excel spreadsheet and see how this actually works. Again, getting a little bit closer to practically applying Kriging to real data examples. All right, I'll see you in the next video.